Okay, so before this, we have discussed on the induced voltage on the, which is from slide from slide 6. We have discussed on the voltage induced in rotating loop. Okay, so this is basically when we turn this wire loop of the rotor inside this stationary magnetic field or uniform magnetic field under the curved pole faces of the stator, as you can see here. Then we found that the induced voltage was 2 VBL. Okay, so that one is the machine that was working as a generator. Now we are going to talk about, I'm going to talk about the machine that is working as a motor. All right, so we are going to discuss on the induced torque in the rotating loop, which is in slide 18 here. So as you can see in this figure, where we now for this rotor, we are going to supply voltage or supply current. This is the battery. For example, we place the battery to supply the current to this wire loop. So to this rotor wire loop, so the current enters from here, which is from DC segment, okay, to the CB segment, and then to the BA segment, then back to the battery. So when we pass through this current to each of the segment of this wire loop inside the magnetic field, the uniform magnetic field under the curved pole faces here, this current will induce force, okay, on each of the segment. So basically this current will be induced force on each of the segment. For example, as you can see in this figure, this is the view from the back side, from this side. So this figure, as you can see in this figure, this is the view from the back side. As you can see, for example, if I place my eyes from here, okay, I hope you can see that. If I place my eyes from here, what I can see from the back side is something like this, which is we have this segment, CD segment, and also AB segment, the other side. So from here, when we supply the current, so from this segment, the CD segment here, the current is into the page, okay? The current is into the page. Okay, so the force will be induced, okay? The force will be induced. So which direction of the force? So we can determine the direction of the force using our right hand rule, FILB here. Using your right hand rule, you will see that the force induced is to that direction, okay, which is perpendicular to B direction. So this is the force induced at segment CD, which is FCD, right? And similarly for the other segment, at the segment AB here, so the force also will be induced when the current pass through this AB segment. So the direction of the force using the right hand rule, you'll see that we know that the force induced is to that direction, okay, to that direction lah. So similarly, this force is also induced perpendicular to the B direction. So as you can see, the force induced also will develop the torque for this rotor part, okay. So when we have force of each of the segment, of course the torque also will be induced. So the direction of the force, so the right direction of the torque is the same direction of the torque is the same direction to the force, okay. So direction of the torque for this AB segment is the same direction to the torque of the, sorry, the direction of the torque for the AB segment is the same direction to the force of the AB segment. Similarly, for the torque TCD, tau CD here, the same direction to the force induced at the CD segment. Okay, so meaning that we know that this rotor is rotating counterclockwise direction. See, So this rotor is rotating counterclockwise direction. So similar to this figure, you can imagine that when the force induced at each of the segment A, B and CD, this rotor will be rotating to the counterclockwise direction. So we can use the same concept to the voltage induced, which is here. When we talk about the induced current, the induced force because of the current flowing in this segment of the wire loop of the rotor. So we can use the formula of FIL cross B lah. Okay, we can use this formula FIL cross B, which is since L and B is perpendicular to each other for the segment CD and segment AB, then we can just use F equals to ILB. All right, and then we can find the torque, which is torque is RF sine theta. If you have a look at this lecture notes, the written notes here, I have explained in more detail compared to the slides. As you can see in the lecture notes here, so we can use this equation, force equals to IL cross B. So we can calculate the force and torque on each of the segment. Okay, segment AB, for example, using FIL cross B, we will get ILB lah, because we know that the direction of L and B is perpendicular. So the force induced is also in the perpendicular direction to the, let's say this is FAB. So we have, this is the direction of the current, for example, which is L direction, and then we have the direction of B, so they are perpendicular to each other, 90 degrees separated. So FAB is the tangential force for the rotor. Okay, as you can see, so using this equation FILB, we can find the torque induced across or induced at the AB segment. Okay, at the AB segment using RF sine theta, since we know that theta is 90 degree, because at segment AB every component is perpendicular to each other, then finally we get RILB for the torque at the AB segment. So for the torque at AB segment there, it is defined as RILB, which is counterclockwise direction. For the segment BC, of course, in our experience, in our past calculation about the voltage or force or torque induced at each of the segment of the wire loop. Okay, so basically when the direction of current or L is perpendicular, or sorry, the direction of L is parallel to B, which is parallel to B here, meaning that when we take L cross B, it is 0. Okay, so the cross product of the parallel vector is 0. Okay, so since the parallel vector of L and B here, we found that the cross product L cross B is 0. So meaning that there will be no force or no torque induced on segment BC here. Okay, so next is segment CD. So segment CD, which is this side. Okay, for segment CD, so basically for segment CD it is the same as the segment AB, which is if we find the force acting on the segment CD of the wire loop, we'll get force is ILB. Okay, force is ILB, and the direction of the force FCD here is the counterclockwise direction. Okay, so similarly when we calculate the torque, okay, using the torque equation RF sine theta, then substitute sine 90 degree, okay, because they are perpendicular to each other. Okay, B, L and F perpendicular to each other. So we substitute with sine 90 degree, then sine 90 degree is 1. We get the torque across CD is RILB, right? So the torque at CD segment is RILB. Okay, and then for DA segment, similar to the segment we discussed on segment BC. Okay, so the segment DA, of course, since L is parallel to B, when we take the cross product of parallel vector, okay, if this two parallel vector, when we take the cross product of these two parallel vector, of course, the force will be induced at DA segment is 0, meaning that when we take the torque, okay, also will be 0. So now we can sum up all of the torque induced at segment AB. So this is the torque induced at segment AB, and this is the torque induced at segment CD. So we sum up all of the torque induced as tau in here. So we get 2 RILB. 2 RILB for the under pole faces, meaning that under pole faces, the torque, the force is counterclockwise direction, right? Under the pole faces, so let's say this is the torque induced, okay? So under the pole faces, which is under this area, the torque induced is 2 RILB, okay? But for the section which is beyond the pole edge, okay, which is I'm showing here, which is this segment, the torque induced is 0. Okay, so basically we know that total torque acting on this rotor is 2 RILB. And then we can further translate this 2 RILB equation into a more something that we can understand, which is related to the behavior of the machine. Okay, the behavior of the electric motor, which is we substitute the value of AP, which is this is the similar discussion when we discuss on the voltage induced. Okay, so for the torque induced also we use the same concept, the same method, which is we define AP as pi RL. So this is the area under the pole. Okay, and then we define phi as APB. Okay, then we get the torque induced. We substitute this AP and phi. Okay, I think we have already discussed this before. So let me just 2 RILB pi RL is AP. So this is very similar to the previous question that we have discussed about voltage induced. So basically when we substitute all of this value AP and phi, we'll see that the torque induced is basically defined as 2 over pi phi and I. Okay, 2 over pi phi and I, which is we can conclude that this motor or this machine working as a motor, so the factors that influence the rotation, the torque induced on this motor is basically based on the factors by flux. Okay, if we increase the flux, the torque will be increased. Okay, and then also influenced by the current. If we increase the current, meaning that the torque also will be increased. So that two variables. And also we can define that this torque also will be influenced by the construction or the physical construction or the material that is used for that machine. Okay, this part represent the machine constant, which just depends on the material, depends on the size, okay, depends on the construction of the machine. So okay, the final torque is 2 over pi phi I. That is the torque under the pole faces. Okay, So next is I'm going to talk about the commutation in a simple for loop DC machine. So I hope that we can finish all of this discussion up to 4.2 here today. So okay, next is about the commutation in a simple for loop DC machine. So basically we have discussed about the voltage induced and also the torque induced for the DC machine, right? Now, I'm going to talk about a simple for loop DC machine. This is for loop system, meaning that we have four wire loop, four sets of wire loop. As you can see in the bottom figure here, okay, similar to this figure, which is as you can see in the lecture slides, the same figure I have redrawn it to my lecture notes here. All right. So now we are considering four sets of wire loop on the rotor. Okay. So that four set of wire loop is represented by, um, for example, as you can see in the figure in the lecture slides here, we have 1 prime, okay, 1 prime entering the slot, okay, and then it will be loop. That is the first wire loop, and then uh, for some number of turns, all right, entering by 1 prime here and then exit at 1, okay, exit at 1. So that is the first wire loop. We can imagine that there is the first set of wire loop, and then the second set of wire loop, which is 2 prime entering the slot here, okay, entering the slot somewhere here, and then exit at 2, which is that is the second set of wire loop, and so on for 3 prime to 3, and then for 4 prime to 4. Okay, so that sort of arrangement of wire loop for 4 loop DC machine. Okay, this is example of the 4 loop DC machine. So when there is 4 loop, there are 4 loop DC machine, there are 4 loop for this rotor, meaning that for the segment of the commutator also divided by 4 segment. As you can see, the segment of the commutator, let me just show you here. The segment of the commutator represented by the first segment, which is segment A, the second segment, segment B, third segment, C segment, and D segment. So there are 4 segments, 4 segments that connects that 4 sets of wire loop of the rotor. Okay, so this is a simple representation of a 4 loop DC machine that we are going to discuss about its commutation process. All right, so this 4 loop representation of DC machine is basically it is in the middle of the, if you are going to understand the real DC machine, of course it will be much more complicated, but for the sake of our calculation, for to easier for us to understand, we are going to consider a 4 loop DC machine here instead of a single loop, which is much very simple, which is we have discussed it before. Then we have already understand about the voltage induced, the force induced, the torque induced, but now we are considering 4 loop DC machine to talk about the commutation behavior of this DC machine when we consider this 4 loop DC machine. So okay, as you can see, this is another example I have shown you in more detail in my lecture notes. As you can see, for example, we have the slot here, okay, and then the slot the other side of the rotor. So the wire enter from here, which is 1 prime, okay, and then it is looped in such a way. For example, you can see also this figure, wire enter from innermost of the slot, okay, and then exit, okay, masuk sini and then keluar. So with some number of turns, for example 100 or 200, 400 number of turns, and then it complete the windings, okay, complete the windings. So one here is the outermost wire. So that is the first set. So actually for the for loop system, it has 4 sets lah. Okay, the first set, second set, third set, and fourth set. Okay, all right. So this is another figure that shows for you to understand better about how the wire is configured. Okay, the wire enters from somewhere here, for example, and then go to the back side and then back to the front side. Okay, wire enter and then front side. So across this segment, the voltage will be induced. Okay? Induced voltage. So for this particular segment, sorry, let me just use another color, green color lah. So this particular segment, no voltage will be induced. No voltage will be induced. So we are considering voltage induced at this segment under the pole faces. All right. So next is you can imagine that at this condition, we consider that this rotation is omega t equals to 0 actually. So at this omega t equals to 0 state, okay, as you can see, based on this figure as well, so this is, as you can see here, omega t equals to 0, right? So we are going to calculate the voltage induced at this state, at this omega t equals to 0, all right? So I have redrawn this to make, which is, I think it is simpler for you to understand instead of referring to the figure that is drawn in the textbook, which is, as you can see in the lecture slides here. So it is drawn like this, but I have transferred it in my lecture notes, which is something like this, as you can see here. Okay, for each of the segments, segment A, B, C, and D, we have 1 prime masuk, entering the slot, okay, and then go to back side, and then uh, out of the slot, go back to the front side here. Okay, so the first winding, the first set of winding connects segment B and A of this commutator, and then similarly from 4 prime to 4, okay, connect A and D segment of the commutator, and then from 3 prime to 3, connect D segment to C segment of the commutator, and then similarly from 2 prime to 2, okay, connects C and B segment of the commutator. And then we are going to tap the voltage. We are going to tap the voltage E, which is E here. I have written there, E. That will be the output. The voltage here is the output of the segment that touch the brush. Okay. Okay, so this is the output terminal of the machine. All right. So as you can see here, since all of this segment, okay, at this situation, we go back to here, this figure. At this situation, as you can see, 1, 2, 3 prime and 4 prime, okay, that one. I'm going to use another color lah. 1, 2, 3 prime and 4 prime are under the pole faces. All right. Similarly, 1 prime, 2 prime, 3 and 4, which is here, also under the pole faces. As you can see, at omega t equals to 0 degree, at this situation, all of the wire loop are under the pole faces, meaning that each of the segment of that fourth set of the wire loop will induce voltage. Okay, so as you can see in this figure, this particular figure that I've redrawn here, there are voltages induced for each of the wire loop, which is across 1 prime and 1 here we have E and this E, okay, and the corresponding direction of induced voltage represented by E, okay. So at this terminal the voltage induced is at this terminal voltage at okay, voltage at 1 2 3 prime 4 prime is out of the page, okay, as you can see here. 1 2 3 prime, susah nak kat sini. 1 2 3 prime 4 prime, 1 2 3 prime 4 prime are out of the page, as you can see. 1 2 3 prime 4 prime, mana 4 prime, 4 prime here is out of the page, okay, out of the page, voltage is out of the page, right? And then for the segment of the wire loop 1 prime 2 prime 3 and 4 is into the page, okay. So we have two different direction actually, which is this direction is into the page, for the left hand side is out of the page, okay. So we get the total induced voltage is 4E, okay, 4E. So as you can see, 2E into the page and 2E is out of the page. So at this particular instant, all right, so we get 4E of the voltage induced across that two terminal of the brush. And then we have here two current paths. As you can see here, there are two current paths. So current will be flowing from positive to negative, which is, let's see, this particular voltage here. So plus is here, and then minus is here, and then plus is here, and then minus is there. So basically when we draw the current path, it should be like this, okay. So the current path will start this from this segment, from A segment, passing through, because this is not connected, this segment is not connected to the brush, right? So this particular segment is not connected to the brush, meaning that the current will pass through this wire and then go to the segment C, okay. That is the first current path. The other current path is, I'm using the different color here. Okay, I'm using the blue color also, okay. The other path is that one, okay. As you can see, it starts from A segment to the C segment. That is the second path of current. So there are two parallel paths of the current. For the current path, we have two parallel paths, and then the voltage is 4E, okay. 2E at this side and 2E at the other side, all right. So that is for the condition at omega t equals to 0 degree. And then similarly, we can calculate when this rotor arrive to another condition, another state here, which is at omega t equals to 45 degree. Okay, at omega t equals to 45 degree, we can see that the area, okay, the wire loop, the segment under the pole faces is 2 4 prime here, and then 2 prime 4. All right. So segment 1 3 prime and 1 prime 3 here is not under the pole faces, which is at this particular wire loop there will be no voltage induced, okay. So as you can see here, across 1 and 1 prime there is no voltage induced. Across 3 and 3 prime as well, no voltage induced, but the voltage will be induced at the segment of 1 prime 3 and 1 3 prime here, right? Okay, So 1 prime 3 and 1 prime at the segment, let's just see the what happened to the voltage at omega t equals to 45 degree at this state. Okay, at this state only two sets of wire loop is under the pole faces. The other two set of wire loop is out of the pole faces, meaning that, okay, as you can see clearly in these drawings, in my lecture notes, written lecture notes here, as you can see, no voltage will be induced at 3 prime and 3 and 1 prime and 1. Okay, but voltage will be induced at 2 prime and 2 and 4 prime and 4. Okay, voltage will be induced at this two particular segment only. So we can say that the total voltage across this terminal, all right, is E equals to 2E. So total voltage E equals to 2E, all right, because no voltage induced beyond the pole edge, all right. So that is the particular direction, the direction of omega t equals to 45 degree. And then it is turning again, okay, it is turning again to another direction, which is 90 degree. As you can see in this figure, I have redrawn back, which is, this is the drawing that shows at omega t equals to 0 degree. So for this case, the total voltage is 4E, okay, and then it turns about 45 degree from 0 to 45 degree, which is at this particular condition, okay, at this particular state of the rotor. As you can see, not all of the wire loop are under the pole faces, so not all voltage will not all segment will be induced voltage. All right, so we have only two segments that will be induced by the voltage, which is this segment and the other segment. So and at this 45 degree condition, E is equals to 2E. All right, and then it turns again to 90 degree, okay, which is, as you can see, 90 degree from the initial condition, which is from 0 degree to 90 degree. As you can see, the segment 1 4 prime is on the left hand side, right? Now the segment 1 4 prime is at the bottom side. Okay, so at this particular segment, the voltage goes back to 4E. See, voltage across the terminal is 4E because all of the parts of the wire loop are under the pole faces. Okay, this one no voltage induced for 45 degree. Okay, only voltage, the induced voltage is at that particular segment. So for this one, all of the segment will be induced by the voltage. So at this particular instant, the voltage will be back to 4E. So okay, so we can redraw the commutation process of this for loop DC machine using this figure. So as you can see, you can imagine that when this for loop DC machine rotates, it is actually start from, this is 0 degree, right? 0 degree here. Start from 0 degree, the voltage is 4E, and then 45 degree, the voltage goes to 2E, and then just temporary, because there is very small slot, there is very small slot for this two pole machine. Okay, for this two pole machine, just a small segment here, which is the wire loop do not receive any induced voltage. Okay, but other parts, okay, under the pole faces, the wire loop will experience the voltage, will induce in the voltage. Okay, so we can redraw this into this particular figure here. At the end, we know that the average of voltage induced is 3E. Okay, 3E is, so E equals to 3E, which is the average voltage induced for this particular behavior of the simple for loop two pole DC machine, all right, which is can be represented by this figure. So okay, to conclude, commutation is the process of switching the loop connections on the rotor of the DC machine just as voltage in the loop switch polarity in order to maintain essentially constant DC output voltage. Okay, so in real DC machine, commutation process takes place to change the polarity what is inside the machine. So what we can see inside the machine is basically the sinusoidal waveform, which is alternating current inside the machine. But the commutation process basically turns that sinusoidal behavior of the current or voltage into the DC output. So that is the basically what we do for the DC machine. We use the commutator to convert the AC behavior inside the DC machine into the DC output. Okay. So the commutator segment basically made of copper bars. Okay, which is copper is better than steel, right? So copper is non-corroded steel, all right. So it is quite a suitable material that can be used as a commutator segment, all right. So if you disassemble a DC machine, for example DC motor, you take out everything and you'll see that that part which is the commutator segment is basically made of copper, all right. And also the brush, okay, brush is the mixture containing graphite, which is carbon lah. That is why sometimes we call it as carbon brush, right? So it is made of graphite, which is durable material, which can last longer. Okay. So this is for the case of machine that use brush. There are some machines, the most advanced machine, there is no brush, which is brushless DC machine, which is work in a bit different concept. So we are not going to cover that brushless DC machine. So in this case, we are considering brush DC machine, right? So I think that's all to cover in this lecture session. So we have covered up to this section, which is the induced torque and also the commutation process of a simple for loop DC machine. There are some tutorial questions that I'm going to discuss later, but basically for this theoretical approach or theoretical discussion, only we will cover this segment up to this, and then next we are going to discuss on the problem with commutation in real machine in our next meeting. All right, so we are going to discuss on the on the problems with commutation in real machine. So in real machine, of course, it involves not only 4-pole but just more than this one. We are considering 2-pole machine. In real machine, there will be more than 2 poles, which is 4-pole machine, 6-pole machine, 8 poles machine. Similarly, for the segment or wire loops, there are 4 loops here we have discussed here, but in real machine, basically we will see more wire loops, more sets of wire loop. For example, 8 loops, 4-pole machine, for example, and then maybe some other more loops, more poles of the machine. Okay, to make sure that the rotation of the machine is smooth. All right. So when we talk about machine DC machine, it involves the current that is we supply to the machine. When the current pass the brush, okay, from brush to commutator, there will be some spikes, for example, will be induced. So the commutation process will be basically experience some problem that we are going to discuss later, which is one of the problem is related to armature reaction, and also the problem in terms of LDI dt voltages. All right. So we are going to discuss on this part later in our next meeting. So basically for this meeting, I'm going to finish now because we are approaching 3 p.m. now. So if you have any question, you can ask. If you don't, as usual, you will don't have any question except you will text me, right? So no problem. So if you don't have any question, let me just end this session up to this time. Okay? Ada? No question, right? QR code. Oh, QR code. Alright. Sekejap. Saya share sekali lagi. Itu antara soalan yang famous ditanya lah. Bila habis session, minta QR code. Okay, silakan. So, yang lain tak ada dah. Okay, so kita habis kat sini. Saya nak stop ni. Jap. Stop.